Yeah, hello.
Hello.
I'm Michael. I'm the co-founder of Zasso, which is a small Swiss company where we make complex scientific applications using mostly JavaScript. And I'm also a member of the TSC in Node.js.
So I'm Luc. I'm a PhD in organic chemistry. That's why I'm here, apparently. And I'm teaching at EPFL, organic chemistry and structural analysis, but I'm also scientific advisor at Zasso. So we will speak today about the challenges of sciences and how did we try to solve those challenges. And somehow in science you have samples, and a sample may be anything. And one of the samples could be a battery. And you will make some measurement because on the battery you would like to know the capacity. So you will use a special instrument. And those data are to be saved somehow. But maybe you're interested to know if the last ecstasy pills that you bought in Dublin is pure or not. Well, we have some instrument that allows to determine if it's pure or not. This is called nuclear magnetic resonance. And it will give you a spectrum, and we need to steer this data. Or you would like to know if the soil is clean or not, and you would like to make electronic microscopy. And like that, we have tons of instruments. At EPFL, we have over 50 different kinds of instruments, and we need to store those data. One of the issues is that those data, they like to invent new formats. And somehow we need to convert those formats. Maybe binary files, it could be text files, and we need somehow to modify it. And what we would like, because we strongly believe that the only application you will have in a couple of years, or even today, it's a browser, we would like to be able to analyze those data, make image processing, image analysis, or comparing many batteries profile directly in the browser. And because we want to use the same tools on the front end and the back end, 10 years ago, 2012, we decided to use JavaScript. And so normally it's pretty easy. You just find libraries and you put them together and you solve your issue. 2012, you don't have libraries. So we had somehow to not reinvent the wheel, but move the wheels or copy the wheels that exist in other languages to JavaScript. And we started to build plenty of little libraries. And of course, because it's ours, they are interoperable, and in science we would call them somehow FAIR. This is an acronym that is being used for data, but they are findable, accessible, interoperable, and reusable. So how many libraries? Over 200. And based on those libraries, we will do funny stuff. So we did it because we need them. And it appeared that we are not the only one to need them. And for example, matrices manipulation, well, we have 1 million downloads per month. Or distance calculation is over 1 million downloads per month. We have libraries for opening TIFF. Because in TIFF, in science, you have 16 bits per channel, and the normal libraries would destroy this information. Or we have some libraries to draw a chemical structure in React. Or some other libraries that allow us to parse files, like IO buffer that allows to manipulate binary files. So all those libraries, over 200, we have over 20 million downloads per month. So we are scientists, and a lot of scientists participate to those projects, so they don't like too much rules. So Michae will add a lot of rules, but most of them will be automatically fixed. So the people that contribute to this project, they don't realize they are completely locked and forced to use plenty of rules. And of course, there will be some problems, so we will add more rules. What kind of rules? Well, the usual suspect. ESLint, temperature, some test case, and things like that. Maybe what's different is that we will use a repository that contains all the rules. So in our 200 projects, we will use the same rules that make sense in our case. And this approach, of course, allows to quickly take over a project. We have 200 projects. Yesterday, I checked on my hard disk. I removed 150 gigabytes of Node modules because I had 500 projects cloned on my computer. So this can also, those rules lead to performance improvement. We advise to have a test-driven development approach. For my point of view, is the fastest way to make the development. And we use at least JSDoc or TSDoc for public methods. So the kind of rules, well, it's kind of basic, I would say. We need semicolon. So, of course, the correct two space for indentations and things like that. Some of them are auto-fixable, like those ones. Some of them will not be automatically fixable, like reduce. We don't allow reduce for different reasons. One of them is that it's not readable if somebody comes from MATLAB, is not used to have reduce, and moreover, it's slow. So those ones will generate some errors, but we will have to fix them ourselves. 2 years ago, also, this was a side effect of a new rule that prevents a wait to be in a loop. And if you fetch data coming from a server, well, with this kind of code, it's sequential. It's one after the other. While if you create first an array of promises and you resolve all the arrays after the loop, well, the browser will fetch all the files in parallel. So you can have a huge improvement, and it's not unusual. We are loading 100 spectra, and those spectra may be 1 megabyte. So it's important to use some parallelism. We also use conventional commits, and the advantage is that to make a release is not just merging a PR, and it will generate the changelog and automatically deal with the different versions. So there is something that we like in science, it's publication. And I don't know if anybody knows Zenodo. Zenodo is a project where you can put data, scientific data, up to 50 gigabytes, but all your code that you published on GitHub can generate automatically a kind of small publication and get a DOI, a document object identifier. I will show you how it works. So a small example, this is a project, and in all our projects, we will have a couple of workflows. The workflow Node.js, it's the continuous integration workflow. What's interesting here is that it's based on a generic workflow. So we have one place where all our project points. So if suddenly there is Node 24 that appears, we change in one place, and in all our project, we will test for Node 24. Another workflow will be the release workflow. This release workflow, the release workflow will extend release please, and will publish automatically on NPM. And then we have the workflow to generate the documentation. So practically, when we make a release in all of our projects, and ooh, what is this? What I need? Okay, yeah, it's Dvorak. That's a trap. Okay, so in all our projects, we will also see the documentation. So this is published on GH pages. So at least based on the TS doc on the GS doc, we will have the content of this library. I was speaking about Zenodo. And in fact, in a GitHub project, you can have a file that is called citation.cff. This is completely standard. And if you have this kind of document that contains an abstract, the authors, this ORCID, if you know what it is, what will happen is that here you get automatically a way to cite your project. So you can copy to LaTeX, for example, the reference if you want to make a publication. But based on Zenodo, what you can also get is a DOI for this specific code. And this is this kind of small publication that is generated automatically each time we make a release. And actually, this cannot be removed. In contrast with a GitHub project that can disappear from the internet, so the source code can disappear, this cannot disappear from the internet. Okay, couple of examples. Oh, no, before some examples, we also play with JS Bench. This used to be the best coffee break. We were sitting in sofa, taking coffee, and fighting what is the fastest way to sort an array. And obviously, if those are numbers, you need to put a callback. And 1 million element is not so exceptional. 1.6 operation per second, it's not super fast. But you have the typed array. And if you use a typed array and a callback, you get 1.7 operation per second. And of course, we may compare with the other engines like Safari or Firefox. Node didn't choose well. OK, now, if you have a float array, there is no reason to put a callback. Because those are numbers. There is no way to sort by string. And if you don't put a callback, you get 7.2 operation per second. So actually, if you use typed array, you are much faster. But the typed array, you cannot make push. This is pretty annoying. But you can create a float array from an array. And if you create a float array from an array and sort, you're still much faster. But you can tell me, no, but at the end, I don't want a float array. I want an array. Well, you can make an array from a float array that is done from an array that you sort. And still, this is much faster. So actually, if you have an array of numbers, it's faster to make this crazy stuff. Good. So practical example, well, we need to parse a SDF file. SDF file, it's a text file. It looks like that. Stupid text file that goes back to punch cards. So it's limited to 60 characters length. So 1 card per line, no? So you quickly have a box of those punch cards. And those are the description of molecules. What's important here is that you have $4 that delimits all those entries, those molecules. And then you have the first molecule and the second molecule. And we have files like that we need to parse with Node. And the little problem is that the NIH in US provides some of those files, but they are gzipped 1.2 gigabyte. So they may be a little bit big. So, oops, sorry. How to solve this? Well, it's your turn, Michael.
Yeah, so I prepared a small project for an example of how we might approach this. And I have here an SDF, which is much smaller than the ones that Luke showed, but still a few hundred megabytes. Let's ls.h molecules. OK, so we have a little bit less than 700 megabytes, which is not too much. You might think that we can just load it in Node. We have enough memory nowadays. So yeah, I'll just do a fs read file sync, and then split using the special separator, and I have my array of molecules, and then I could simply log the first one, and in a real life, it would be a code that processes each of them and put them in a database or something. So let's try to run it. Well, it doesn't work. And you might not know that, but in V8, there's what I find a really low limit for the length of a string, which is about 500 megabytes if it's all ASCII. And yeah, that's what we get. We cannot just load it. So instead, we're going to use something that has been a kind of recurrent thing these days. It's streams. So I'm using here relatively new API from Node. I think it's from Node 20, fs.open_as_blob, which will create a web blob that I can use to generate a web stream. Then I'm using the gzip version in this case. So I pipe this web stream of bytes to a decompression stream. And since this is a text file, I will then decode it with a text decoder stream and just async iterate on that, and we will see what we get. So yeah, we just have the first few hundred lines of this file. And then what's cool about WebStream is that you can easily create your own. We had a session yesterday afternoon learning how to do that. So I created a transform stream, which will basically accumulate the chunks until it finds the separator and enqueue each molecule in the stream, and so then when we iterate on the final stream, we will get one molecule after the other if everything is done right. So here I have one entry, and yeah. Then, as Luc said, we care a lot about making code that also works in the browser. So most of this should work in the browser, but we are still importing FS to generate the initial stream. So to make it completely browser compatible, I made a last version, and for that, I just created a little Express 5 server with a single route that always returns my data. And to get that, the data, I use fetch. And when you get a response from fetch, you have body, which is a readable stream, and then the rest of the code is the same. We pipe everything. And this time, I will just, for good measure, see how long it takes to process those molecules one by one. So Node. Okay. So we actually parsed this file and just went through all the molecules, which is a large number, more than 300,000, in less than 2 seconds. So it's quite fast. And we can take that code, go in a web browser, just run the same code, and we get the same result, which is, what I find interesting is that it's actually slower in Chrome. I would have expected the opposite, because they should implement everything in a native way, but, well, it's faster. Web streams seem faster in Node. And that's it for the demo.
So yeah, that's an important point, is that I think 90% of our libraries are compatible with the backend or the front end. And now that web streams are available, we can use it. So this means we could parse files of 5 GB that would not be possible in the browser before. Good, small application, a funny one. It's based on Wikipedia. In Wikipedia, you have chemical molecules. This is the active drug of ecstasy. So this is MDMA. And there in Wikipedia, you have this kind of drug box or chem box. It's something that is structured. And the idea is to provide a way to query for chemical structure. So this kind of connectivity, we want to provide a tool that allows to make what we call substructure search in chemistry. So every night, we will go in Wikipedia to find all the changes about molecules that have been done during the day. But we didn't feel too much like hosting a server and manage a server, so we will simply use GitHub. And in reality, a GitHub action can be scheduled. So we can say, OK, every night at 3:30, you will run this action. And in this action, well, we will run Node. So we will go in Wikipedia, we will find all the changes, and we will create a database. And actually creating the database is simply committing a data.json. The database is simply a JSON file. But moreover, because we make a commit, we will also trigger Cloudflare so that it rebuilds the website with this new database. And what we did, it's the possibility to make those queries directly in the browser. So the point here is that this is being hosted by Cloudflare. What I just did is to load the database of this night. So currently 21,000 molecules. I don't need internet access. They're there, so you can scroll. All those 21,000 molecules are in the browser. So we had to create a component, a React component to display a molecular formula, a React component to display a chemical structure, but also a React component to make what we call substructure search, to look for a specific pattern. And also this query is done in the browser. So there is really no interaction with the server. We had to do all this logic in pure JavaScript so that it works like we want on the front end or the back end. So that's a first funny application. This is open source. You may have a look how we did it. Another one is the more advanced application that we did. And our idea is to be able to replace the software that scientists use to install on their computer with a web-based application. And this application is reusing 80 of our dependencies. So that's a relatively big project. In green is the one that are downloaded over 100,000 times per month. In blue, it's over 10,000 times per month. And this application allows to process those NMR, nuclear magnetic resonance spectra. Again, all the processing will be done in the browser. And I have here a small example of coffee. It's a coffee data set. Actually, they're counterfeit coffee. So the way it works is that the Colombian coffee is 100% Arabica. And it's worth more than the Robusta that is produced in Brazil, for example. And so there is counterfeit coffee that goes from Brazil to Colombia, and then they try to sell it as Arabica because it's worth more. So there are some models that allow us to find out if it is really Arabica or not. And those kind of experiments, it's nuclear magnetic resonance. That's the experimental data. You see, it's quite verbose, a lot of files. Actually, this folder is pretty big. So it's a big hierarchy. So we have 4 GB of data and 12,000 files. And the idea is to open them. So what we can do is to take this folder, drag, drop on an Emerium, and we will load the spectra. So the system was able to scan for those 12,000 files, the one that should be loaded. Those are binary files, convert them in SVG. So each of those spectrum is 128,000 points. And in this case, we have 77 spectra. So it's nearly 10 million points that we have here. And you can start to manipulate them. You can start to measure the surfaces under some peaks. But this is fully web-based. And we can see the surface under the peaks. We can sort spectra based on the surface, just by a single click. Or if you want to find some selectivity, maybe there are some specific peaks, there are some specific peaks related to this Robusta Arabica. You can define some mathematical formula. I don't know, A minus B divided by C minus D. And so it will add a new column. But all this is done quickly in the browser. And actually, it's even difficult to find an application that is as fast, even if you need to install it. So JavaScript is, I think, pretty fast. And that's the kind of application that Zassodium is doing. So that's it. Thank you for your attention.
All right. Any questions from the audience? If not, that's okay. Oh, all right. One moment. Question over here.
Hi. Great talk. Thank you for that. I was just wondering, obviously Python is kind of like the king of scientific computing, I guess, at the moment. Is JavaScript and Node.js kind of like a little bit of a niche in your area, or is it, are you actually managing to make it grow and solve these problems in the way that you have and really demonstrate that it's a valuable language to use for this sort of thing?
I think it's completely niche. Nobody really learned JavaScript in science. So at EPFL, where I'm working, it's 100% Python. But I don't know how they will make web application with Python. And that's our point, is that if you want something user-friendly, interactive, well, it's better to develop everything directly in JavaScript. But on the other hand, this is the reason why we had to publish 200 NPM packages, because nothing existed. So, yeah, we are promoting this, but...
Second question, if I want to avoid MDMA in Dublin, where do I not go? Tell me that.
I would also like to know, so I can avoid it.
Yeah, I was going to ask pretty much the same thing about Python, but the key advantage, as far as you see it, is the ability to publish to the web and share everything on the web, yeah? Another thing I was wondering about is, I know Dino recently added a Jupyter kernel to their runtime. Is that something that's available in Node, or that would be useful for Node to have?
But, yeah.
Yeah, it would probably be something useful, but I also learned about the Dino announcement, but I was not aware before that that it was possible to make custom kernels. So, yeah, if someone wants to develop that, it would probably be useful. Yeah.
Yeah, I also found out that there is a package that allows to execute all the JavaScript, have a Jupyter notebook, but where all the JavaScript is done in the front end, and execute it in the front end. Because to come back on Python, we have an issue with GPDR and the police, where they are not allowed to upload identification documents that are not anonymized. And what we did with those libraries for image processing and things like that, AI, to anonymize the document in the browser before it leaves the browser. So they are sure not to have any personal information going to the database or leaving their browser. So that's also a reason not to use Python.
Wonderful. Any other questions? All right.